He's talking about superradiance. He's also currently writing a book on the matter, Black Hole Superradiance from Fundamental Physics to Astrophysics. It's going to appear this year.
Hopefully.
Hopefully. So, okay.
Thank you. It's a great pleasure to be here. Thank you, Silke, for being such a wonderful host. It's my first time in Nottingham. Campus is wonderful. I'm enjoying the city very much. I'm going to tell you a little bit about the work in the last 5 years or so that the group in Lisbon, together with collaborators elsewhere, have been doing. Let me mention especially Emanuele Berti, in Mississippi, Richard Brito finishing the PhD in Lisbon. I think my pointer is not, oh yeah. Finishing PhD in Lisbon, Leonardo in Rome, Akihiro Ishibashi in Tokyo, Hirotaro Kawa in Kyoto, Paolo Pani in Rome, Franz in Princeton, Thomas here, Ulrich Perrak in Cambridge, Helvi as well, she was a PhD student 2 years ago in Lisbon, and Miguel currently in Barcelona. I hope to make this informal enough that we can get something useful out of the discussion. Mostly, I'm going to be summarizing these two works. And the work has been, mostly in the last 5 years, trying to understand strong field dynamics in a highly relativistic, highly nonlinear regime. And there are several reasons why you would want to do that. The first is, of course, that black holes exist. We know, we've been monitoring the center of the galaxy for decades now. We know that there's a supermassive, highly compact object there, something with around 4 million solar masses. And we also know that the least exotic explanation for that is that we have a black hole of around 4 million solar masses at the center. In the last 5 to 10 years, at least a couple of experiments are aiming at looking closely in the electromagnetic spectrum, the Event Horizon Telescope, aiming to do black hole shadows. They will, at least they promise, a resolution of around 30% in the light ring. Whereas Gravity, a German experiment, is already taking some data. This is one of the things they can do. Since some years ago, they started monitoring this highly ionized cloud of gas passing close to the center of the galaxy. This is the year. As years go by, you see the cloud passing close to the black hole. It got disrupted last year, got tidally disrupted. Parts of it fall into the horizon. Parts are scattered to infinity. And so, you know, it's, I think, the perfect timing to understand, to start thinking about strong field problems. Of course, here, the black hole geometry is really just a background, but there's other motivations to understand really the strong field gravitational dynamics. The traditional one is gravitational wave astrophysics, trying to understand black hole powered phenomena, and most especially trying to understand gravitational wave detection. Now for this, you have to know very precisely the waveform coming out of the merger of two highly compact objects, for instance, two black holes or two neutron stars. The reason why you need to do that is not because, well, I mean, the waves are being generated. The reason you need to be highly precise about waveforms is because of the way you actually dig out the signal out of the noisy output. And the traditional way we have to do that is called match filtering, and it involves cross-correlating the output against a family of templates. So you generate templates, so you give me a couple of black hole masses, couple of black hole spin, you generate a template, you cross-correlate against what's coming out of the detector, and if you have a very good family of templates and the signal is there, eventually you're going to be able to know that you're looking at the gravitational wave signal. Okay, that's the traditional reason to understand the waveforms out of the merger of two black holes, for instance. This can look just like boring physics, but if you try to dissect what's coming out of such binaries, you'll see something like this. This is a signal for generated numerically for two equal mass black hole binaries starting at some distance. And it's basically comprised of three stages. The first is quasi-Newtonian. We call it the in-spiral phase. So you have two guys orbiting around each other on a quasi-circular orbit. They release energy under gravitational waves. They slowly in-spiral. The amplitude, this is the gravitational wave amplitude versus time. The amplitude increases. The frequency also increases. Eventually, the pair merges, and you form a single highly distorting black hole, which is basically releasing gravitational waves and settling down to the final stationary configuration of the field equations, which is a Kerr black hole.
What is the second before the inspiring? That's just one little peak. Numeric?
Yeah, this was, as I said, this is a completely numerically generated waveform. And still in 2015, we don't know how to deal exactly with the initial conditions. This means that, you know, to start the simulation, you need to tell the initial data to the code. And there is no way to generate precise initial data, you have to know the entire past history of the binary. We don't have a clear way to do that, so whenever you prescribe initial data, it always comes with some arbitrary gravitational wave content, which we call, you know, spurious or junk radiation. So forget about this. Of course, you need to make sure that this is not going to disturb the dynamics of the binary at later times, but you can do that. So people have been doing that. Okay. Now, one of the interesting stages in the life of a binary is the last stage, at least for me, because in this stage, it doesn't really matter how you formed the final black hole. This stage, which we call the Ringdown stage, always looks the same. It's always a superposition, which to a very good accuracy is a linear superposition of quasi-normal modes of the system. It's not precisely a normal mode, it's a quasi-normal mode because this is a dissipative system. But it means that if you measure the decay time scale and the ringing frequency of the signal, it's going to depend only on the black hole parameters. But in GR, black holes have no hair, which means that the signal, whatever it is, can only depend on the black hole mass and spin. Now, this means two things. So first, if you measure a single ringdown mode, you basically find two quantities, the decay time scale, the ringing frequency. You can, in principle, invert to compute the mass and spin of the black hole. Okay? If you measure two or more modes, then you're in business, and you can actually start testing GR. Are these modes distributed in the way that GR predicts, or do you get some imprint of extra physics in that? Of course, the level to which you can perform these tests depends not only on the signal-to-noise ratio of the gravitational wave in the detector, but depends also on how large the modifications to GR you think they are. But you can do it in principle, okay? In fact, you can show that even with advanced LIGO, you're going to measure black hole spin and masses to within a fraction of a % level. It's awesome. You can basically map the mass and spin of any black hole that LIGO sees to within 1%. Okay? And so this was, and still is, the fundamental reason why we want to understand extremely dynamic black hole binaries. You can also start asking fundamental questions. For instance, is cosmic censorship always preserved? And one of the ways you can try and see if you have censorship at all times is by taking a couple of black holes and trying to collide them as violently as you can. Okay? We know that in GR, Kerr black holes always spin, well, they spin very slowly, or at least the angular momentum is bounded from above by a certain number. Let me call it 1, okay? So what I'm trying to do here is take two black holes, collide them with a finite impact parameter at very large speeds, Now, if they have an impact parameter, there's angular momentum in the space-time, and what I want to see, or what I may want to see, is if it's possible to give too much angular momentum to the space-time and not create a curved black hole. Have something there which simply has too much angular momentum. Okay. Now we've done this some years ago. So again, I'm going to take two black holes. I'm going to throw them at one another at roughly 93% of the speed of light. It's a very, very violent collision. And I tuned. So what we see is that if the impact parameter is too large, well, you get what you expect. The guys approach each other, and at some point they just scatter to infinity. Okay? If the impact parameter is 0, they collide head-on, you get what you expect, you form a single non-rotating black hole. So the question is, what happens when I start decreasing the impact parameter? Still with a huge angular momentum initially. So I'm going to show you, colors depict the amplitude of gravitational waves, and they are initially here. You will see an initial wave pulse coming out of the holes. This is not physical, this is exactly what I was discussing. We have no control over the initial conditions. I can talk a little bit more about that afterwards, but the initial pulse is not physical. So angular momentum in the space-time, they circle one another. They are attracted gravitationally. They circle one another a couple of times, but there's simply too much angular momentum in there. If they try to merge and form a single object, that object would be spinning above what we call the Kerr bound. It would not be possible to be a black hole. It would have to be a naked singularity. Okay? Let me repeat this because I find it very nice. Gravitational attraction, they orbit around one another. Too much angular momentum. They zoom out. They are still releasing energy and angular momentum. Finally, it's safe to merge because they basically release the excess angular momentum. They merge and they form a highly spinning black hole. In fact, somewhere along here. Okay, it's a different family of initial conditions, but somewhere around here. This shows you the total radiated energy in units of center of mass energy as a function of impact parameter, and this shows you the final angular momentum of the final black hole as a function of impact parameter. Again, these are units where the maximum possible value for angular momentum of a black hole is 1. Okay? What you see, and these are initial data for which the velocity of each black hole in the center of mass is 75% the speed of light. What you see is that you can get up to, in this family, 30% of the center of mass energy released as gravitational waves. It's a huge efficiency. Huge efficiency. And what you also see is that as you decrease the impact parameter from very large numbers or increase it from very small, the spin of the final black hole increases, but cosmic censorship is preserved. Okay? This is the lesson here. You get up to 96, 97% of the maximum possible value for the spin.
Vitor, what are the other spins that you have?
Well, these are different estimates for the spin.
From the gravitational waves?
Yeah, from ring-down modes. It was a very nice tool to see from energy conservation and from apparent horizon data. These are different estimates. These different lines are different ways to estimate how rapidly the final black hole is spinning, because you need to have some diagnostic tool. Okay, and they agreed within 1% or so. Okay.
All the initial angular momentum is angular, right? It's orbital. I mean, there is no. So all of the initial angular momentum.
Yeah, the black holes are non-spinning. In fact, one of the things you can test with this is the conjecture that only the mass matters when you form. Only the mass matters at sufficiently large center of mass energies. For instance, if I repeat this experiment at very large center of mass velocities, but now I put the black holes initially spinning in a random direction, when you increase the center of mass energy, details about spin are irrelevant. So at very, very large center of mass energies, the only thing that matters is the energy. Spin, charge, everything else is washed away.
So it also doesn't matter if they are orientated or not?
No, it only matters if they are aligned or anti-aligned at sufficiently small center of mass energy. For instance, if you repeat it for these values of the velocity, and now you put some spin initially in the space-time, you will see some differences in these lines. I don't have a slide for that, but I could show you. You will see a difference. But as this velocity goes from 75% the speed of light to 95% the speed of light, those differences are washed away. You see that very, very nicely. Yeah.
What would happen if you put it in a box? You seem to be losing angular momentum in the gravitation.
Yeah.
Stuck in the box.
That's a very good question. I'm going to partially answer that. But there, so, yeah. Well, let me go soon enough to that, yeah.
But what about the, I mean, what if they collide with a very low velocity?
Right.
And then if they would have opposite spin?
Oh, it makes a huge difference.
Could it even happen that they don't merge or that they...
No, so what happens, so you're trying to, break cosmic censorship. So if you put too much spin, people have done this. If you align the spins so that you basically increase the total angular momentum in the space-time, and you throw these guys at one another, what you will find is that they stay on what people call hung-up orbits. They will orbit one another for a much, much longer time while they release all the excess angular momentum until finally they can safely merge and form a single, highly spinning black hole. So they don't scatter, they just wait until excess angular momentum is released. Okay?
Do they merge immediately after having gone past the bounds? Or like when they have too much angular momentum in the beginning?
Well, immediately it's always on a quasi-circular orbit or elliptical orbit of this kind that you saw here. Yeah. But so what I'm going to focus now on the rest of the talk is not on, so these were all vacuum simulations, vacuum situations. What I would like to, start to understand now is what happens when you put fundamental fields, or in this case fields which are otherwise stable, around black holes, and you put them in strong field gravity. Are there any new phenomena that could be interesting, that could give you some bounds on the field itself or not? And specifically, I'm going to focus on energy extraction mechanisms from spinning black holes, which I will very loosely call superradiance. And I'll show, well, I'll try to argue that when superradiance is put into the game, you can even form new stationary solutions of the field equations, meaning no-hair theorems are not really, are not really valid when you allow some dynamics, at least for scalar fields, okay? And I'll show you how and why this is interesting to constrain the masses of, hypothetical massive bosons, and also to understand very nice gravitational wave imprints of these systems. So let me start by telling what I understand by superradiance. It's a very old phenomena. It was, people thought about it much before we dealt with it in black hole physics. I think the first example that I know of, at least, that deals very specifically with waves was actually done in fluid mechanics. So you have two media. So there's a planar interface here. So let me call it z equals 0. And there's two fluids, one here in the upper part and one in the part below, okay? Now these fluids are moving relative to one another with a relative velocity which I call u, okay? The experiment I'm going to do is to send in a sound wave in the fluid below, which say it's at rest with respect to us, okay? And see how much I get back from it. So how big is the reflected amplitude of this sound wave? I'm dealing with a sound wave, okay? This calculation was done here. It's very nicely summarized by Landau and Lifshitz. And what you will see is if no dissipation enters the game, then the reflected amplitude of this wave is larger than the incident wave if this medium is moving supersonically. Okay? So no dissipation means you get amplification when you have superluminal or supersonic motion. Okay? And this, I think, was the first example of what I'm going to call the translational superradiance. Although, well, I'll go afterwards to this one. In fact, you can repeat this kind of reasoning and show that the Cherenkov effect is really just superradiance. I think the first person to put this on a very nice thermodynamical form was Bekenstein in '98 or so. And there's an entire class of systems that you can put in under the hat of superradiance. Okay? I discovered some months ago that even before the rotational superradiance example was given by Zeldovich in the 70s, there was a very nice experiment done some kilometers away from here in Birmingham, which was basically trying to provide for an electron beam amplifier. So you have an electron beam here. Okay, this was for radio systems in the 40s. And what the person this was Kompfner. The theoretical study was done by Pierce, 47. By the way, in the same year, Ginzburg explained the anomalous Doppler effect, which is a very similar effect to this one. But anyway, what he did was the following. He sent an electron beam, so here, and the idea was to accelerate the electron beam by extracting energy away from an electromagnetic pulse. Now, what you understand from this experiment is that you need some kind of supersonic motion, right? But you can't have supersonic motion, not here. So the idea was to basically artificially reduce the speed of light by making the light travel on this spiral waveguide. Okay? So the effective speed along this direction is smaller by a ratio of p over a. And therefore, if you tune sufficiently the parameters in the system, you're able to basically exchange energy between the electromagnetic wave pulse, which travels here, and the electron pulse here. It's a very nice, I mean, I think it's an ingenious idea. And it works. But this is not rotational superradiance. I think that the first example of rotational almost superradiance is something very familiar to all of us, and it's called tidal dissipation. Tidal dissipation is basically the rotational analog of something like this. So consider the system Earth, Moon. Let me put an ocean because now whenever I cannot have superluminal motion, I need dissipation, and I'm going to show you why. Okay? So the Earth is rotating along its axis, the Moon is revolving along the Earth, and it so happens that the angular velocity of the Moon is smaller than the rotational velocity of the Earth. What this means is that there are tides generated on the surface of the Earth, and that they lag with respect to the Earth-Moon axis by some angle phi. Okay? And they lag because there is friction between the ocean and the surface of the Earth, right? So the Earth is spinning like this, the Moon is spinning in this direction but slower, right? Now the Moon generates tides, but because there's friction, they are always lagging, okay? And because there's friction, there's energy being extracted, and to conserve angular momentum in the system, because there's no other force there, to conserve angular momentum in the system, what must happen is that the Earth slows down and the Moon gets farther away from us. And this has been measured, okay? So we know that the Moon is getting farther away from us at the reason of 1 millimeter a century or so, okay? This is tidal dissipation. It doesn't really, you don't really need waves to do this, because you don't need to be farther from the wave zone to do this, but it's kind of the analog. The exact analog would be something like this. So I have some wave around a rotating body, I'm going to assume that there is some coupling between this wave. So by the way, I'm showing you here some multiple in the wave. There's a coupling between the radiation field and the rotating body. And the way you would translate this scenario here would be basically to compute the angular phase velocity of the wave and compare it against the rotational velocity of the body. And if the angular phase velocity of the radiation, which is given by the frequency over the azimuthal number, so over the let's call it the phi dependence of the wave, if this is smaller than omega, then again the radiation field is lagging the body and it's basically exerting a force over the body. It wants to spin it down. It means that radiation is being exchanged between this rotating body and the wave. This guy spins down, the amplitude of the wave grows. Okay? And this is superradiance. So you don't need a black hole at all. Okay? In fact, one of the first examples, actually the first example of rotational superradiance was by Zeldovich in '71, and he introduced a very, an ad hoc model that I'm going to focus on for a minute or two here, which is basically consider dissipation. You need dissipation always if you want to have rotational superradiance. Okay? And the idea was to model dissipation by modifying the wave equation. Well, the idea is to introduce a term that is inspired by the heat equation. Okay? In the absence, so if you take off the time operator from the box here, you basically get the heat equation, and you know that any fluctuation is damped on time scales of 1 over alpha. Okay? So I'm going to do that here as well for 1 minute. So let me assume I have a spinning star, okay? And the star is interacting with some field, okay? And inside the star, this is what I consider. This is what I should be considering, okay? If the star is non-spinning, you can solve this equation very easily. It will show you that the field is damped inside the star, okay? Now what I'm going to assume, the only thing I'm going to assume is that this equation is valid only inside the star and only in a medium at rest and only in a frame at rest with respect to the star, which is where you usually measure these parameters, okay? And outside the star you have the usual Klein-Gordon equation. This is 0, okay? So the way you do this in practice is you solve the Klein-Gordon equation, the regular Klein-Gordon, this is 0, outside. Then you change to a frame which is co-rotating with the star, and you solve it inside. Now, what you realize immediately, and this was, Zeldovich understood it very nicely, is that when you do this, it's equivalent to go from a coordinate time t to one which is basically t minus, the rotational velocity of the star. And this means that for sufficiently small frequencies, it's equivalent to having a negative alpha. Instead of dissipation, you have amplification. I mean, so you didn't even need to do any calculation to predict that there must be superradiance. But anyway, if you do it for a star, what you get is, so I'm going to expand the solutions at infinity in this way. This represents, with this time dependence, this represents an ingoing wave, this represents an outgoing wave, and what you find is a ratio A out over A in, which I will call the reflection, the amplification factor, shown here. So this is amplification factor versus the frequency of the wave in a problem. And it does show you that when alpha is non-zero, you always get amplification of any wave. Now, of course, the big objection is, does a realistic object, can you model a realistic star interacting with a scalar field with this term? I have no idea. Okay, it would be nice to actually, get more physically motivated dissipation terms in this, but this shows you that it's very generic. You don't need black holes to have superradiance. Of course, when you have black holes, dissipation is built into the problem. It's built into the problem because black holes have a one-way membrane, which is event horizon. And because you have dissipation, you have superradiance. And one of the things that you can also have, and now going back to that point, is if you surround, so you have a black hole here, you throw in a wave, it's amplified, and of course, if you surround the black hole by some cavity, you need to, it's basically forcing the radiation to go back and interact again, and you're going to have an exponential cascade of energy in the system. And well, some people, and I adopted the terminology, call this the black hole bomb. Okay, it's an exponential growth in the energy density of the radiation field.
This wave is going radially in.
Yeah. I mean, this is just, so call it the.
Send it a little bit.
Yeah.
It's in, and then you would bend pulse.
Yeah. So, well, I'll show you that next. You have to have some non-trivial angular profile to have this. Yeah. Okay. So, of course, this is a very artificial system, right? But on the other hand, when you're solving the Klein-Gordon equation for a field which has a non-zero mass term, the mass term effectively produces a finite amplitude barrier at large distances. So it's kind of a semi-transparent mirror at some finite distances. So you would expect to get a similar phenomena, and in fact you do. So this is the effective potential for wave propagation of a massive scalar field in the background of a Kerr spacetime. Okay, so basically we put the equation in a Schrodinger-like form, and what you get for the effective potential is this. So you get a potential that at the horizon goes to 0, it's constant at large distances, but due both to rotation and to the black hole mass term, there is kind of a well at a finite distance. The well typically is located outside the black hole ergo region, but it has a tail, so the field develops a tail that goes inside the ergo region, and so it's tapping energy. Well, ergo region is a ergo region represents the stationary point in the black hole spacetime where observers cannot be at rest, and where you can also have negative energy states. Okay, and so basically the field develops a tail that can extract negative energy away from the black hole, and it grows exponentially close to this point. Okay, so the idea in the end is if you do a Fourier analysis of the field, you will find unstable modes, and the unstable modes are characterized by this formula. So mu is the mass of the field, okay, in units of the Planck mass. What you find is that the unstable state rings at a frequency close to the mass of the field. So this term mu omega is very similar to mu, and then it develops an imaginary component. If you remember, so let me remind you that the field has this expansion. Okay, so if omega, if a normal mode of the system has a positive imaginary component, it means that the system, the amplitude is growing exponentially as time goes by. Okay. Now the imaginary part is proportional to mu to the 9. So for very small scalar field masses, this will give you a very large instability time scale. It takes a lot of time for the field to grow to appreciable numbers. Okay. But at least at the linear level, you found a way to destabilize a Kerr black hole. Okay. Of course, you can have already, even at linear level, interesting things, because the first thing you need to consider is this is a linear level calculation, and of course what everybody here will tell me is that if I do nonlinear effects, then at nonlinear level you have an induced quadrupole moment, then therefore the system black hole plus scalar field outside is emitting gravitational waves, and so at nonlinear level you're going to have to eventually quench the growth of the field, right? However, if you're working with complex scalars, you will see that you can avoid this. And the reason is very simple. If the field is complex and you have a time dependence which is of this form, then the stress tensor can actually be spherically symmetric. You can have a zero induced quadrupole moment in the scalar cloud, let me call it this way, okay? So it seems possible, at least in principle, to build truly stationary solutions representing a spinning black hole and an oscillating scalar field outside, if the scalar is complex, okay? This is all at linear level, okay? And by the way, at linear level, this is a simulation we did a couple of years ago with LVWTech. What you get is this. You start with a very generic scalar field profile outside a highly spinning black hole. The black hole is spinning at 99% the maximum possible value. And what you find is something like this. This is like a dipole exponentially growing. If you follow this for a billion dynamical timescales, you will find this guy is indeed growing exponentially, okay? But it's linear. Now, at nonlinear level, the first, I think, interesting remark, yeah?
What was the initial setup of the field? Was it the Scalar field? I mean, what are the azimuthal numbers here?
Yeah, so the azimuthal number for this one is m equal 1. This is an L equal m equal 1, and it's a Gaussian distribution centered at r equals to 12m. Okay, and the width of the Gaussian, I think, is around 1 in units of the black hole mass. So you have the spinning black hole, you put this guy away, well, very much away from the ISCO. Okay, so the guy is at 12m, and it has a width of 1, basically. It's a kind of, you always get this kind of development for...
does it have a radial component? No, has a radial component?
Yeah, it has a radial. The radial component is a Gaussian. The angular component is this one. It's a spherical harmonic with L equal m equals 1.
And then if you go to higher L azimuthal numbers, you have them. I mean, have you done these simulations also for m equal 2 and so on?
Yeah, yeah. So of course, if you start with an L equal m, if this is a spherical harmonic, and you start with a L equal m equal 1, after some time you will find also L equals m equals to 2, L equals 2, L equals 4, m equals 2. You will find combinations because spin couples the harmonics.
Because you have the strong gravity and at the linear.
Even at linear level, the angular wave functions that separate Kerr are not spherical harmonics; they are spheroidal harmonics. And spheroidal are a linear combination of spherical. So you would get different multiples anyway. But yeah, you also get this for higher multiple numbers.
That's slower, I guess.
But the growth is slower. Yeah. But so the first surprise happened last year when Herdeiro and Radu actually discovered new hairy solutions of Einstein equations minimally coupled to a massive scalar field. The mechanism is exactly this. The field has to be complex, but if the field is complex, we presume that the end state of the instability may be one of these solutions. The reason, so I'm parameterizing the solutions here. Again, mu is the mass of the field, m is the ADM mass of the black hole, j the ADM angular momentum, and q is the scalar charge because there's a scalar current here. Okay. And what the interesting thing about these solutions is that for some parameters, for some scalar field mass and scalar field charge q, the quadrupole moment of the system can be extremely large and very much larger than the quadrupole moment of the Kerr black hole, which is this line here. So this is all normalized to the Kerr quadrupole moment, which in these units is 1. Okay? And because you can measure quadrupole moments, you can in principle have sizable deviations from the Kerr geometry. Of course, when the quadrupole moment is extremely large, what you have in practice is a very, very large and extended scalar field configuration with a small black hole at the center. And these configurations actually join smoothly to boson stars, meaning to configurations which only consist on scalar field. Okay, and these are truly stationary solutions of the field equations. Okay? So this solution is, I think, is a nice example first of all, of how you can break these no-error theorems without breaking them, because the field is time dependent. And then, it's somehow the missing link between boson stars and black holes. Now you have a way to join a curved black hole to a boson star very smoothly.
Can you just run us a bit more detail what a boson star is?
Yeah, a boson star is basically a solution, a nonlinear solution of the field equations for a minimally coupled massive scalar field. You have, I think, at least 3 different types depending on if you add a quartic term in the interaction potential or not, and this can give you more or less compact configurations. But even if you solve just the minimally coupled massive field, you have a regular solution of the field equations.
Without a horizon?
Without a horizon, yeah. According to some people, Q balls would have an extra interaction term. They would have a 5-4 self-interaction term. These are only 5 squared. The potential here is only 5 squared, okay? Right. Now, whether or not these solutions are interesting, I think it's still very much an open question. The reason
looked at the superradiance in these solutions?
No, so they had a paper today broadly discussing the stability of the solutions. I very much think that at least a fraction of these, so at least the upper...
Rapidly rotating.
Right.
There's arbitrary, I mean, if there is arbitrary rotation,
Yeah.
it's still an error correction. There is still
right, exactly.
That's because they have a quadruple.
Yeah. So in part of this parameter space, I would bet something that they are unstable, because they will be rapidly spinning, and they can be rapidly spinning. So this is in this diagram. These are curved black holes. These are boson stars, and these are, well, the hairy black hole configurations. So you can still have highly spinning configurations which extend very much outwards. They have ergo regions, you can show that. And therefore, you expect these solutions also to be, again, unstable against some kind of superradiant mechanism. But this has not been shown. Okay? The other question, which I think is perhaps even more relevant, is how do you actually grow these guys? I mean, do these guys come up of the nonlinear development of the superradiant instability or not? I'm going to try to argue next that they don't. At least most of this parameter space cannot appear as a result of the nonlinear evolution of superradiant instability. But still, it's a very interesting, completely open problem. So what I'm going to actually try to understand now is how exactly this instability grows nonlinearly. So I'm going to do that in 2 ways. One of them I'm not going to show you, and it would involve the nonlinear time evolution of the Einstein field equations just with a minimally coupled scalar field. We've done this not as well as we should have, because you can only evolve this for so long. And because these time scales are huge, the current infrastructure can really not handle this. You will have to evolve these systems up to 10 to the 8 or 10 to the 9 dynamical time scales, measured in units of black hole mass. And current codes are still not able to do this. You can evolve it up to 1 million or 10 million dynamical time scales, but that's simply not enough to see the instability growing and the space-time asymptoting to some new solution. Okay? I'm going to try to argue that you don't need this, actually. So I'm going to include now gravitational wave emission in the game, and I'm at linear level, and I'm going to include accretion by some hypothetical accretion disk around the massive black hole. Okay? And what I want to know is if hairy solutions are formed, and if the linear instability, when you study it at the nonlinear level, still gives you energy extraction away from the black hole, okay? Or can it be that accretion is simply putting too much angular momentum into the black hole, that superradiance is just not interesting, okay? So my scenario is the following. I will consider a spinning black hole. Then around this black hole I have this, let me call it a scalar cloud, a cloud that's growing, let's assume, by superradiance. Because I want the field to be generically real or complex, I'm going to include gravitational wave emission in the game, so this system is emitting gravitational waves. And at the same time, I'm going to assume, because we know most black holes are surrounded by accretion disk, that there is an accretion disk whereby matter falls into the black hole and tries to spin the black hole up. Okay? I'm going to assume that the accretion disk is co-rotating with the black hole because I want to be conservative. I want to have a mechanism that tries to spin the black hole up and not down because superradiance is spinning the black hole down. Okay? So again, to be conservative, I'm going to assume a very optimistic scenario for the angular momentum exchange between the accretion disk and the black hole. So this is perfect angular momentum transfer. The matter, this is, by the way, a classic Bardeen-Thorne model for accretion. Okay? So the accretion goes all the way up to the innermost stable circular orbit of the black hole, and from there onwards it transfers mass and angular momentum. So the only thing you need to do is to compute parameters at the innermost stable circular orbit of the black hole, okay, and grow the black hole from there. Okay. So the only thing you need to do is to compute specific angular momentum and energy at the ISCO, and the angular momentum transfer by accretion is related to mass transfer through accretion through this formula. Okay? I'm going to parameterize accretion with a parameter which people call the Eddington luminosity parameter for the black hole at the center of the galaxy. This guy is very small, meaning it's not a luminous black hole at all. This is 10 to the minus 9 or so. But again, I'm going to be conservative and take f to be between 10 to minus 1, 10 to minus 4. I'm going to model gravitational wave emission in a completely relativistic way. In fact, this is an interesting system where even though the cloud is rotating non-relativistically, so the angular velocity of the cloud, so to speak, is Newtonian, but you cannot apply the quadrupole formula here. It's an interesting example of a system where the radiation wavelength is much larger than the system and therefore is incoherent. You need to be very precise when you compute this guy. Okay, but anyway, if you model this carefully enough, you will find that the flux under gravitational waves is given by this expression, where ms is the mass in the scalar cloud. Again, m is the black hole mass, mu is the scalar field mass. Okay, and of course, angular momentum emission under gravitational waves is related to the energy emission under gravitational waves by this formula. Okay. So what you find is the following. Let me start first with a mass. Let me be specific. I'm taking a field with a mass of 10 to minus 18 electron volt and an Eddington parameter of 10 to minus 1. And I'm going to start with a black hole which is spinning at roughly 0.6, the maximum possible value. Okay? Now it happens that for this particular system, the black hole has initially 10 to the 4 solar masses. The coupling parameter m mu, and this coupling is what governs how strong the instability is. Okay? It so happens that for this system, that coupling parameter is very small. So the instability takes a long time to act, which means that initially accretion is much more important. So initially what you find is that the black hole spin, so this is dimensional spin, the black hole spin grows due to accretion. Of course, if the black hole is spinning up, the mass is also spinning up, which means that if this coupling parameter is initially small, the coupling is growing. So at some point, the superradiance kicks in. Okay? It suddenly kicks in, it extracts very rapidly the angular momentum away from the black hole, and suddenly it goes on this critical superradiant line where it's quasi-stationarily evolving in a way that mass accretion and angular momentum emission evolve on that critical, evolve on the critical superradiant line. Okay, so the system along this line is marginally stable against superradiance. Okay, and the bottom plot shows you the mass in the scalar cloud as a function of time in units of years. Okay, basically we evolved this for a Hubble time scale. And what you can see I think for any of the simulations we ran, the maximum mass in the scalar cloud is around 15 to 20% that of the black hole mass. Okay? Well, of course you get different time evolutions if you start with different black hole mass and black hole spin. This is one example. Here I'm starting with a 10 to the 7 solar mass black hole, so the coupling is already big. It means superradiance is active initially, and therefore the system, the black hole spin does not grow up by accretion. It stays roughly constant because superradiance is trying to steal energy away from the black hole. Accretion is trying to spin it up. Okay? Generically, generically you will find the following. If you want to understand how a typical black hole evolves, you need to be a bit more sophisticated, so we started doing Monte Carlo simulations. We took 10 to the cube the black holes with the initial mass and spin distributions being random, okay? And we want to look at what happens at the spin and mass distribution after, say, a Hubble timescale. And what you find are, well, what you suspected, which are gaps in the Reggie plane angular momentum versus black hole mass. And these gaps exist because for a field of 10 to the minus 18 electron volts, you cannot have a black hole spinning above a certain threshold if the black hole has a mass of, say, 10 to the 7 solar masses. Why? Because for this field, if the black hole has a 10 to the 7 solar masses, the dimensional coupling m times mu is so large that you steal all the rotational energy from the black hole on scales of a year or a week or 10,000 years, not more than that. This means that on Hubble timescales, the black hole should not be spinning, period. Okay? Right? It also shows you another thing, which is if the scalar mass, if the mass in the scalar cloud is at most 15% of the black hole mass, and I should remind you that this is a scalar field which is extremely extended, the density in scalar field is extremely small, so you can trust all these calculations. You do not need, so my point is, you do not need fully nonlinear evolutions to understand the development of this particular system. Yeah?
What I don't quite understand it. I mean, superradiance is a stimulated process, right? And you want to see how it mines angular momentum, but it also depends on, you know, I mean, I don't know what the initial configuration is. I guess in this case it's given because I could say if I want to mine faster, I just have to send in more. Yeah. So how does this come up here? I mean.
Yeah. So superradiance is a stimulated process, but this is not this is an instability. This means it's a spontaneous process.
So the initial configuration doesn't matter.
Doesn't matter. Yeah. Yeah. Anything you put in there will basically grow exponentially. So it doesn't really matter the specifics of the initial detail. Now, why is this important? This is important because if I look out there and I see a spinning black hole, it means I can constrain the mass of the hypothetical scalar field out there, okay? And this is the game we played 2 years ago or so for vector fields. So this is a very simple Proca equation, which you can solve again in the background of Kerr. We took observational data. This is from Laura Brannaman and al. And what you find is that the best constraints, so let me summarize this plot first. This is black hole angular momentum versus black hole mass. You measure astrophysical, so you observe astrophysical black holes, you put them on this plot here. These are observational errors, okay? Now, the windows here represent systems. So if a system is above this blue line, it means that the rotational energy of the system is extracted on time scales smaller than 10,000 years. Okay? This means that on time scales, sometimes of days, the black hole should spin down to values smaller than this guy. So it should be somewhere here. Okay? In other words, if you observe a black hole within this window, it means that the field cannot have this mass. Okay? For example, the observation of these 4 guys, or 5, within this blue line, means that the scalar field has to be, the mass of the scalar field has to be smaller than 10 to the minus 18 electron volt. Why? Because if it's smaller, remember the important coupling is black hole mass times scalar field mass mu. If the coupling is smaller, the instability time scale is larger, and you could still have time to be observing the guy, right? And this also means that this guy here, which is Ferrel 9, it has a mass of 2 10 to the 8 solar masses, tells you, well, if you trust this very clean calculation, tells you that there cannot be vector fields with a mass of 10 to the minus 20 electron volts. They have to be smaller. And if there were no dirty effects in astrophysics, this would be the end of it. In fact, if you open the particle data group booklet, this number is 2 orders of magnitude smaller than what you find there. So it would be an incredible bound that you get just by using supermassive black holes. I think it's incredible, okay? Of course, as usual with things that are incredible, it's too good to be true. And because this is a vector, you need to worry about couplings to accretion disk matter or intergalactic plasma and so on and so forth. Okay? It's not a clean calculation. However, if you repeat this for gravitons in most of the consistent theories, massive gravitons, the calculation is clean because we know they interact very feebly with matter, and the bound that you will obtain is 10 to the minus 23 electron volts. It's still a very, well, it's not the most competitive bound, but it's a bound that is completely independent from any other bounds that you get on the graviton mass, and it's still competitive, okay? Just by observing highly spinning supermassive black holes. Okay, so let me finish this talk. I think there's there's a lot to do in strong field gravity. I think it's the next 5 to 10 years will be amazing, especially when you start getting data from electromagnetic telescopes and gravitational telescopes. There's a lot to do. I think there's a rich phenomenology to understand in the interaction between black holes and fundamental fields. Very specifically, I hope I convinced you that superradiant instabilities can provide strong, sometimes model-independent constraints on the field masses. New hairy solutions can arise, and going back to the question of what happens if you put a black hole in a box, we don't know. I think one of the biggest unsolved problems is evolving black holes in what people call anti-de Sitter spacetimes. It's not done, it's extremely difficult framework to deal with. But one of the things we are convinced is that you do find new black hole configurations. And just by giving mass to the field, I think it's one example of a semi-transparent boundary that you can have there. So, well, I think there's a lot to do. Thank you for the attention.
Did anybody consider fermionic fields outside of black holes?
Yes.
Then what other new phenomena?
So, yeah, fermionic fields don't have superradiance. The reason that you usually find the excuse is the exclusion principle, right? So you can't occupy more than one state, so you can't have amplification. The calculation bears exactly the same result. At linear level, there is no superradiance. And therefore, you also do not find bound states around black holes. So I think all of this only applies to bosons. Yeah.
Yeah, so
just let me add, because it's one of the things that I'm also interested, but it's much more complex, so I don't know how to deal with it. Which is, I don't know what happens when you couple a fermion, say, to a Maxwell field. Maxwell fields do have superradiance. And so I don't know if at nonlinear level you can either develop an instability or you can develop bound states. I don't know, it's a tough problem. But so, yeah, sorry.
Yeah, so it's a question about putting the bound on the graviton mass. I mean, you know that when you have a light graviton, but not zero mass, there's a very low effective field theory cut off in the theory.
Right.
So I'm just wondering, I don't know, I have to check the numbers, but the equations that you're using here, are they actually valid?
I have no idea. I have no idea. I took the equations, we take the equations at face value. So, yeah.
I mean, so there's two effects, right? The first effect is that it's, you can just ask literally when the quantum corrections become one.
Right.
It's always at a much sort of lower scale than you might anticipate. That's the most serious one. But then, of course, also there's even that manifests itself classically through things like the Weinstein mechanism.
Right.
The classical field space themselves become nonlinear at a larger scale as well.
I don't know, that's an interesting problem. We haven't touched on that. Yeah.
So probably the bound is a bit dirty than how you can expect.
Probably, yeah. But I have to say that all, yeah, I don't know, I think all the bounds that you can find, at least the relevant bounds that I found on the graviton mass, all come from kind of either the Fierce-Pauli equation or some very ad hoc model for the equations, right?
Right.
So,
of course, we know now how